Hello, this is the second part of the least squares methods, and we today talk about the simple two-dimensional example for applications of these methods. So here we are given a solution, or we are looking for a solution of matrix equation AX is equal B for given matrix A and vector B. Unfortunately, this system is inconsistent, so the exact solution does not exist. And I would like you to actually, I strongly recommend you to actually show that this system is inconsistent. But again, we're trying to find the closest approximation to this solution. And as we discussed in the previous video, there is normal equations which we can use to find such an approximate solution. So we need to actually find our product of our transpose matrix A to the matrix A on the left-hand side. So then on the right-hand side of the formula, we have transpose matrix A multiplied by vector B, and we will try to solve this equation. Okay, let's try to find all the matrices necessary to solve the normal equations. And we start by multiplying transpose matrix A on itself. So, and again, to transpose, we take the columns, convert them into row, multiplied by the matrix A itself, and we have 2 by 2 matrix here. Okay. Now let's look at the right-hand side of the normal equations. Here we need to find the product of transpose matrix A by the vector B. Again, write transpose vector A multiplied by the vector B, get vector of 2 entries. Okay, so let's just try to remind ourselves what we're trying to solve. So we are actually solving this normal equations, which is identical to, we already identified the matrix on the left-hand side. It should multiply with vector X, which should have 2 components. Let's call them X1 and X2. And on the right-hand side, we should have this vector, which I color-coded in red. Okay, how we can solve it? Of course, we can reduce it to echelon form, but it's only 2 by 2 matrix over here, so it might be easier to actually find inverse of this matrix. So our vector X hat will be the product of inverse matrix on the left times the right-hand side. Okay, let's find this inverse matrix, and again, we will use a determinant solution here. And if you're not sure how to do it, please refer to chapter 3, which discuss the methodology of it. Okay, so we have now the inverse matrix. So let's find our approximate vector X bar. So we write our inverse matrix and multiply it on the right-hand side of our normal equations, transpose matrix A times B, and then simplifying things a little, and here it is. We find our approximate vector. So our approximate solution using the least square here is a matrix of vector 1, 2. And it's just approximation. Is it a good approximation? We actually do not know, but there is a way to calculate. We can calculate the error or the distance between a solution and its approximation. So here, let me give you a little sketch of our problem. So we have our vector B. It's over here. It's 2, 0, 11. And as you can see, it's rather far away for our column space A. So what we did actually, we find the projections, and its projection is given us by the product of our matrix A by approximate solution X ahead. So if we find the distance between the projection and the vector B, that will tell us what kind of error we're making while using an approximation. And again, it's okay to use an approximation, but we have to be very clear of what kind of error we make. Okay, let's calculate the the approximate solution, which is the product of our matrix by the vector x hat. So it's basically the right-hand side of the approximate solution, or in the previous section we'll call this vector b hat. Okay, let's talk about vector A multiplied by the vector x, which we find in the previous question, and we will receive the solution vector in the column space A. Okay, so what we're looking is the difference between our solution and orthogonal component. So we can take our vector B right-hand side and subtract the vector b hat. And again, we have now three components. So, but what we're interested is actually the distance between our vector and approximation. So let's calculate this distance again using the Pythagorean theorem. So, and it helps us to estimate the length between our vector b and the projection of its vector on our column space, which happened to be square root of 84. So we can report that we find the vector x hat, approximate solution 1, 2, and the error for our solution is the square root of 84. Is it appropriate or not? We do not know. We need more information to make that conclusion.